Hey everybody, how you doing? Today we're going to be talking about species diversity. In the last lecture we talked about genetic diversity, which is the amount of genetic variation that occurs within a single species. Today we're going to be talking about diversity among species and specific species number. Okay, so I'm just going to start sharing the screen and we shall sort this out. Here we go. Okay, so by the end of this class, you guys should be able to describe the components of species diversity. You should be able to practice measuring species diversity with real situations, to compare diversity and formulate predictions and how they match calculations of actual values of diversity. So as I said, I better set up the. In the last class, we talked about genetic diversity. So we talked about genetic diversity almost as a static process. So we looked at how do you measure the amount of genetic diversity, or what is the genetic diversity that takes place in the species. But genetic diversity isn't static. Over time, new mutations are occurring inside the genes of species. And as a result, we get this sort of incremental change. And over time, genetic diversity, sort of the divergence of individuals away from their original form, can produce new species. And one of the classic examples of this is finches. So if we look at things like Darwin's finches, so this is what the founder species looks like. Over time, they evolve to start to focus on different types of food. As a result, the species diverge away from each other. This is due to genetic change over time, and you end up with very, very different looking species, such as the Nihoa finch and the Amakahi. So over time, incremental change in genetics can lead to the formation of new species, and therefore we can have different numbers of species in different environments. But we now need to think about, well, how do we measure the diversity of species? Is it just the number of species, what we call species richness? So can we think of genetic diversity as just, okay, different numbers of species? Well, I mean, species diversity, different numbers of species. Well, let's have a look. So, I hope that at least one person in this class recognizes what these fish are. These are known as Lake Malawi cichlids. So Lake Malawi is a lake, it's just shown here, in Africa, in landlocked Malawi. We've got Zimbabwe down here, which I've got a lot of fond memories of. Zambia, Tanzania, and then Mozambique here. And Malawi is this landlocked country in the middle. And Malawi is most famous for this giant lake, Lake Malawi. So just like the US, Africa has its own series of Great Lakes. And also just like the US, these lakes are being formed by the continental plate literally pulling in two. So as the continental plate is pulling in two, it's creating this valley. This valley is filled with water from the Zambezi River and others. And as a result, we've got these gigantic lakes. I mean, they are absolutely enormous. And Lake Malawi is really rather famous because most of the fish that exist inside Lake Malawi belong to this group of cichlids. So this is an image from an aquarium of Lake Malawi cichlids. Lake Malawi cichlids are an incredible story because what happened was a group of cichlids of one species swam up one of these rivers while Lake Malawi was forming. These fish found themselves in this sort of empty lake that was devoid of fish. Because remember, this lake was never connected to the ocean. It's formed by the continent pulling in two. So this group of fish swam up a river and found themselves inside Lake Malawi. When they got there, they realized, didn't realize, but they were the only fish in the entire lake. And so what happened was that initial species started to evolve, and it eventually produced 650 individual species. So just in Lake Malawi alone, there are now 650 species of closely related cichlid. Just for context, that's more freshwater fish species than there are in the entirety of the continent of Europe in one lake. And these fish, these are them here. You can see they all have the same basic body shape. They're all sort of this sort of oval shape with the dorsal fin and the caudal and the anal fin, and then there's the caudal fin. And let's see, we've got this guy. This guy is a totally different species, but same shape. You can see here the fin shape is very similar. Here's a white one. These ones are different sizes, different shapes, or different sizes and different colors. But they're all basically cichlids. There's just 650 different species of them. Just for context, and in case anyone is stuck for something to do, it's estimated that only about half the species in Lake Malawi have ever been described. So if you're looking to name a species, Lake Malawi cichlids are a good place to start, because you can basically go in that water, and if you have the time, you can actually describe a new species. The reason all of them aren't named and described is not because they can't be found, it's because it's just a Herculean task to name them all. So as a result, this place has got 650 different species. But let's have a look at this image here. Yes, we see lots of different species. We see these yellow ones, these sort of light blue ones, these dark blue ones, these stripy ones, these white ones. We see a whole bunch of different species. But if we look at the numbers of individuals of each species, it looks like all species in this image are quite abundant. So we've got lots of these yellow ones, we've got lots of these light blue ones, we've got lots of these grey ones, we've got a few of these dark blue ones, we've got slightly fewer of these stripy ones, but still a lot of them. So although we have a lot of species, the number of individuals in every species seems relatively even. It seems like the same sort of numbers of each. So do we measure species richness based on the number of species or the number of individuals within each species? The best way to do it is compare it to something else. So here is an image of the coast of British Columbia in Canada, just off Vancouver Island. This is a place called Bamfield. I taught a field course up at Bamfield for a long time. It's a wonderful part of the world. It's absolutely stunning. But this is an image of the intertidal zone off the coast of Bamfield. And so let's count the number of species we've got here. So we've got mussels in the background, and we've got absolutely loads of them. There's probably 500 to 600, maybe even 1,000 in this part here. Then we have this type of seaweed, this type of macroalgae. It's a bit of it here, bit of it here, bit of it here, bit of it there. So we've probably got about 7 or 8 individuals of this macroalgae. Then we've got this other form of turf algae. This looks like there's more of it than that macroalgae, so there's quite a bit of that as well. Then we have a few barnacles. There's one here, 2, 3, 4, 5. These are the big, huge, what they call whale barnacles. Then we've got these tiny little barnacles, and we've got hundreds of those. So look, there's tons of them just down there. And then in the foreground, we've got this gigantic starfish, Pisatster. So it looks like we've probably got 5, 6, maybe 7, even 8 different species. But we have hundreds, if not thousands, of mussels, hundreds, if not thousands, of these little barnacles, tens of these bigger barnacles, and maybe less than 10 of this macroalgae and about 10 of this macroalgae as well. So although we've got lots of different species, if we look at the number of individuals of species, we've got everything from just one individual of this species to potentially thousands of individuals of this species. So if we compare that difference in these two communities, in this community, yes, we've got lots of species, but we also have lots of individuals of each species. In this community, we've got a few species, but we've got very different numbers of individuals within each species. Okay, so we then have to think about how do we really measure diversity? Well, there are 2 components, and these components are what we call richness and evenness. Richness is just the number of species. We just count the number of different species. So if we think about richness, what that means is, as soon as we see one individual of a species, we count that as 1. If we see 10,000 individuals of one species, that also just counts as 1, because we just count the number of species. Evenness, on the other hand, is a measure of the relative number of individuals in each species. So let's take a look at it here. Here we have 2 images. We've got a coral reef, and we've got the wet forests of Washington State. You can see in this, we've got the coral reefs are, of course, incredibly diverse. We've got lots and lots of different species of coral. We've got a large number of species of fish. But if we look at the coral in particular, it looks like we've only really got one individual of each species. apart from these two cauliflower corals, maybe these two here. But generally, it's a very high diversity, but each individual coral, there's only very few individuals. So I've got high richness, and in coral diversity, relatively good evenness. Each coral species has about the same number of species, same number of individuals. You compare that to these forests in British Columbia, sorry, not in British Columbia, in Washington State, we can see that, yeah, we've got quite a bit of diversity. We've got these massive, gigantic trees here. These are probably cedar. We've then got all these ferns down the bottom, and then we've got this moss that covers absolutely everything, and a few epiphytes here. So let's think about the richness. We've got at least one big tree, 2 for the ferns, 3 for the mosses. Oh, it's a pine here, so it's 5, a couple of epiphytes, so 6 or 7. But look at the difference in the number of individuals. We've got 4 massive cedars. We've got probably hundreds of ferns, and then we've got millions potentially of individual moss stems. So the richness would be 5 or 6, but the evenness is wildly different because for some species, we've got many, many more individuals than we have for others. Okay, so just to reiterate this. So richness is things like richness, which is denoted by the letter S, is the number of species. We just count each number of species. So we compare the two of these. So for example, this is a hill slope in a place called Guanacaste in Costa Rica. It is one of the most biodiverse places on the entire planet, especially for plants and trees. And this is Logan Canyon, which is a pretty place. And it's, you know, it's a nice natural area, but it hasn't got nearly the number of species. So if we count the number, if we just count the number of tree species in Guanacaste, Costa Rica, oh sorry, the Upper Chagres River in Panama, places, that's literally around the corner from where I was talking about. So if we count the number of tree species in Panama, compared to the number of tree species in Logan Canyon, we see we've got nearly 300 tree species in this part of Central America, and we've probably got 30 to 40 tree species in Logan Canyon. So just based on purely on richness, yes, we could say the Upper Chagres River in Panama is far more diverse than Logan Canyon. But now let's have a look at evenness. Evenness is denoted by this letter J, and it's a measure of the relative abundance of different individuals. And the reason evenness is so important is it's often used to assess impairment or pollution in rivers. So for example, here we've got 2 different sites. We've got one site which is immediately outside of the discharge from a sewage plant. Here we have another site which is this pristine, beautiful mountain stream. This is the community of animals and macroinvertebrates that live in these 2 locations. So in both these samples, we have the same number of species. We've got a mussel, gammarus, shrimp, we've got a snail, and we've got a mayfly. 4 species in both places. We've also, in our sample, got the same number of total individuals. We found 18 individuals in total across all of them. But look at the difference in how they're distributed. So in this, in the effluent, the vast majority of individuals, it looks like 14 of them, were this one species of mussel. Then we find 2 shrimp, 1 snail, 1 mayfly. You compare that to this pristine stream, and we've got what looks like 5 mussels, 5 snails, 4 gammarus, and 4 mayflies. So although we have the same number of individuals in both sites, and although we have the same number of species in both sites, we have a very different relative abundance. So based on that, which would you say is more diverse? Would you say this is more diverse or this is more diverse? Because think about it. In this sample, the vast majority of individuals were all one species. In this one, it was much more balanced. So when we talk about evenness, the more balanced, the more equal the relative abundance of species, the more diverse the site is. So we have 2 components: richness, which is denoted by S, and evenness, denoted by J. Okay, so let's do a quick fake clicker question. So just think about this in your head. What best describes the relationship between diversity, richness, and evenness? So richness is the number of species, evenness is how similar the population sizes are. Diversity can be measured as one or both. Or B, diversity is measured as richness. C, diversity is measured as evenness. Or D, diversity is independent of richness and evenness. Let's give you 10 seconds. 5, 4, 3, 2, 1. Okay, well, I would hope that most of you got, yes, richness is the number of species. Evenness is how similar population sizes are. And diversity can be measured as one or both. Okay. However, there are these magical values called diversity indices. Now, I'm sure several of you had a minor heart attack when I first opened this slide, because it's covered in mathematical notation and things like that. We are going to go through this. It's going to be easy and it's going to be fine. A lot of people just instantly panic when they see mathematical notation, but it's just like trying to read something new. And what we're going to talk about is a diversity indices. So a diversity index is something which is a number which incorporates both richness and evenness. So it's a measure of both at the same time, distilled into one number. Okay. One of the most common of these is the Shannon Diversity Index. And the Shannon Diversity Index is measured as this value here, H. And it's denoted by this formula here. Okay. So let's go through this formula in bits, starting at the beginning. So the formula is, well, we know what a minus is. That's just, it makes it negative, or positive, it's already negative. This piece of notation here, this is called sigma. And sigma just means is the sum of. Okay, if that makes any sense. So what we're doing is we're looking at the sum of, and we're looking at S. And S is, remember, species richness. So what it means is when you see sigma and you see a little a number or a symbol at the top here, this basically means the sum of for all of these. So we're looking at the sum of for all species. And I just equals 1, so that's our species number, basically. The rest of the formula is pi, so we say p number 1, multiplied by the natural log, which is a value on your calculator or on your scientific calculator using a computer, pi. So it's just the sum of pi multiplied by the natural log of pi, where pi is what we say is n over I, where n is the number of individuals of that species, and n is the total number of individuals in our entire community. We're going to go through this really slowly in the next couple of slides, but I just want to introduce you to all up front. So what that means is the Shannon Diversity Index is the sum of what we call the relative abundance of each species multiplied by the natural log of the relative abundance of that species. So pi, this value, is just the relative abundance of species I. We get that by dividing the number of individuals in species I by the total number of individuals. So Ni, as I said, is the number of individuals in species I. N is the total number of individuals of all species. S is the total number of species. And species evenness, we can then back calculate from this value by taking this value divided by the natural log of species richness. If our Shannon Diversity Index, if it's 0, that means all the individuals are the same species, and high values equals high richness and all individuals are evenly distributed. Okay, so let's just have a go at this quickly. So here we have a very simple community of fish. We've got this big lake and it contains a community of fish that's 100 individuals there. Believe me, I put them in, there are 100 individuals, but they're only of 2 species. So it looks like we've got 50 of this species and 50 of that one. We also have another lake where, again, We have same number of species, only got 2, but now it's much less even. We've got loads of these red ones, only one of the green ones. So when we eventually work this out, we'll go through it in a bit, but our evenness in this J is roughly equal to 1 because both the numbers of species are identical. In this one, the evenness is much lower. So although we have the same number of species, this one has a much higher evenness. And our Shannon diversity index for this one is calculated as 0.70. This one's calculated as 0.06. So we can see when we look at these with our eyes, we can look at it and say, yes, this one, they've both got 2 species. This one looks a lot more even, but if we work it out mathematically, we end up with these values. So let's actually do this. So remember, the relative abundance of each species, which is Pi, is equal to the number of individuals of that species divided by the total number of individuals. So let's do it this way. So that is the number of green fish divided by the total number of fish. So in our first community, it is 50 individuals divided by 100 individuals because we've got 50 green fish and there's 100 fish in total. In this community, it's 1 number of green fish divided by 100. Okay, so that's how we calculate the relative abundance of the green fish. Remember well, I don't expect you to remember it, but just to reiterate, this is what our Shannon diversity index is. It's just the negative of the sum of the relative abundance of species I multiplied by the natural log of the relative abundance of species I. So the easiest way to do that is actually not to write it down like this, but this shows you what the total formula ends up being. What we end up is, it's -1, because that gives us our negative at the beginning, multiplied by the relative abundance of the green fish times by the natural log, the relative abundance of the green fish, plus the relative abundance of the red fish multiplied by the natural log, the relative abundance of the red fish. Because the reason we add them together is because we have this sigma. Remember, this means the sum of. So what does that look like? Well, let's see. So the easiest way to do these is actually to build yourself a little table and fill in each bit. So we look at the number of individuals. In this case, we have 50 green fish and 50 red fish. Therefore, our relative abundance, Pi, which remember is 50 divided by 100 for the green fish and also the same for the red fish. Pi is 0.5 for both species. The natural log, so remember you do this by doing it in your calculator. Actually, let me just see if I can actually do that. Give me just 2 seconds. I will find a calculator on my computer. Applications, calculator. Let's see, can I put it into scientific? Yes, I can. Okay, I'm just going to change the screen for a second. I have to stop sharing, and I'm going to share. Hello again. I'm going to share the screen and show you a calculator. So here is my calculator. Remember, our relative, let's do the green fish. Our relative abundance of a green fish is 0.5. If we then do the natural log of this, we end up with negative 0.693, but you just take it down to 2 significant figures, so 0.69. So that's as easy as it is to do the natural log of something. Okay, I'll stop share and go back to the actual presentation. There it is. So in this case, yeah, we work out our relative abundance, we work out our natural log, then we do the relative abundance multiplied by the natural log of the relative abundance, we end up with this value, negative 0.35. So that's this multiplied by this gives us this. We do that for both species, we sum it together, and we get a value of negative 0.70. Remember, we then minus that so that we, because we do it by -1. Why are you not actually going? And that gives us our Shannon diversity index of 0.70. If we do it for the other community, now we've only got one individual of the green fish, So its relative abundance is 0.01. The natural log of 0.01 is negative 4.61. If we multiply these together, we get 0.05. For the redfish, we've got 99 individuals, so its relative abundance is 99. We multiply, so its natural log of 0.99 is negative 0.01. If we multiply those together, we basically get negative 0.01. Sum these two together, and we get negative 0.06. Multiply it by -1, and we get our Shannon diversity index of both. And remember, to calculate this evenness, or J, you divide the Shannon diversity index, you divide that by the natural log of the number of species, in this case 2, so we end up with a value of 1, and this one we end up with a value of 0.09. So that is how you calculate the Shannon diversity index. Now, in an exam situation or in a quiz, I'm not going to ask you to actually go through and calculate the Shannon diversity index. However, I do want you to know what the index is, what it does, how it operates, and what it tells us. So although you don't need to actually be able to calculate it yourself, you do in a quiz. I might ask you to do it in a homework because you can refer back to this slide as you do it, but you must be able to have an understanding of what it is and what it does. And that is basically the way that we measure the diversity of species. I use the Shannon Diversity Index in a whole bunch of my research projects that I do right now. It is a well-used and well-known piece of calculation. So as I restated, by the end of this class, you guys should be able to describe the components of species diversity, practice measures of species diversity with real situations to compare diversity, and also formulate predictions, assess how they match calculations of actual values of diversity. Okay, and that is as far as I wanted to get to today. So I will see you next time. All the best.